Hi everyone, should we start now? Are you able to hear me clearly? Hi Abhinav, hi Balaji, hi Bintao, hi Kamal, hi Noor, hi Rosh. Should we start now? Great, great. So I'm going to take out this one. So, all right. So where were we last time? Till the last point? Anybody? So yesterday we talked about how to handle the situations where you have nonlinear relationship with the data. And the interesting part is what we did was we basically added the polynomial feature. Okay. So what does polynomial features do? It basically adds more data to your input data. Okay. Say for example, here it has added the square of this. Okay. So it's a 2-degree polynomial. So it has basically added one more variable. Okay, if there are two columns here and two columns here, so what it'll do is it'll add the square of it, then it'll also add the square of the second one, and then it'll also add the multiplication of the two. Okay, so that way it basically makes your input data have more columns from the existing one. So it'll add more values to the existing one, and then you can simply fit the linear regression. So essentially, the polynomial features say basically. So polynomial regression is essentially linear regression, just that it has more dimensions. Okay, so that's how we solved the polynomial um, more degree kind of models using the same linear regression. Okay. All right. So if you have n features and you are introducing more features using the polynomial features transformer. So if you have n features already and you are adding I mean, you are adding the polynomial features with the degree d. So in the end, after transformation, you will have n plus d. Okay, n plus d and factorial divided by d factorial and n factorial. A question from Bintao. So far, we only deal with univariate variable, and will we learn about multi? Yeah. So basically, the whole thing that whatever we have learned so far is actually for multivariate. Okay. Here, this is basically the. Let me go back. So when we learned earlier about the data, let me just show you about whatever work we did. Everything is everything is valid for multivariate. Okay, everything is very valid for multivariate linear regression. Okay, let me see. Is the voice problem with everybody else? Okay, so we talked about all of these parts and we were talking about polynomial regression. A question from Noor. What is the difference? Difference is, okay, univariate means our equation has only one variable, as in y in terms of x. Okay, that's univariate. There could be x1, x2, x3, x4, x5, and so on, right? So if n equals 1, that means we have univariate, while n is more than 1, that means it's a multivariate. Okay, yeah, multi-features, correct. Wonderful, wonderful. So what we discussed last time was that using polynomial features, what we can do is we can introduce more features to our existing data set in order to deal with the polynomial, in order to interpret our data as polynomial regression, okay, in which it's not linear, it's polynomial. But the interesting part is that after introducing the polynomial features, we are able to solve the problem using the linear regression itself. Okay, all right, I hope the voice is clear to all of you, because I checked my audio device. Great, great. So this was an interesting part whereby all we needed to do was needed to add more features to our input data, and then in using the polynomial features function, uh, polynomial features transformation or transformer of scikit-learn, and that way we can introduce as many features as you want. Okay, based on what degree we provide. So all we did was did degree 2 and said include bias. Right now, since we had in the input only one feature, so it added one more. If there were two features, let's say point 0.1, point 0.2, so it'll add point 0.1 square, point 0.2 square, and point 0.1 into point 0.2. Okay, so all we are looking at is, if you take a look at this data, what we are saying is that the coefficients are still linear. Okay, the data is non-linear, but the coefficients are still linear. Okay, have we written the equation for the polynomial regression yet? All right, let's just go ahead. Okay, so this is something that we talked about. And if you have two features, A and B, polynomial features with degree 3 will add these more features. So it'll add A, A is already there, so it'll add A square and A cube. Then B is already there, and B square, B cube, and AB, A square B, and AB square. All right. So now, once we have done this, we can do the linear regression, normally linear regression, and fit the fit the data as usual. Okay. Once we do that, we'll get the results, and this is what we got. So this is C, the bias, or you can say X naught, and this is the X1 and X2, X1 and X2. Okay. So this is the intercept. Okay, and these are the coefficients. This is 1.7 dot this, and these are the coefficients. All right, this is for x1, this for x square. So this way you can always solve your nonlinear the polynomial regression using the linear regression model. Okay, and it is fitting perfectly. You can see that it is fitting perfectly. The next thing that we talked yesterday about high degree polynomial. So when we come to linear regression of this way, so what you have noticed is there will be just too many features. Most of these features are derived features, correct? And derived features from others. Now, here, there are high chances of overfitting and underfitting. Okay, so we need to be able to distinguish between overfitting and underfitting. Okay, also we'll understand what does it mean by overfitting and then how to tackle overfitting. Tackling underfitting is easier. Tackling underfitting is basically we introduce more polynomial features and that's how. But tackling overfitting is hard because of many reasons. So we'll go into more details about how to tackle the the overfitting problems. All right, we'll talk about regularization and other parts. Okay, so we had talked about this part and we talked about, so let me just go over it again. As we've seen earlier, high degree polynomial regression fits the training data. Okay, much better than linear regression. In this case, the second degree polynomial fits really well. But what happens when we put more degree polynomial regression, as in let's say the 300-degree and so on. So here what we have is for the same data with the Gaussian noise. So this was our actual equation, right? Not this. Um, where was the original equation? Yeah, here, right? So the original equation was 0.5 x squared, meaning x squared by 2 plus x plus 2, right? So with a little bit of Gaussian noise. So x is generated randomly, okay, and we have some kind of a noise. So ideally, when you draw this plot, it generally comes like a curve. But since we have added noise, so it looks like a hazy curve, right? So and after adding the polynomial features of second degree, uh, we are able to fit the curve very well, right? This is the second degree polynomial. Now, what happens in case we try to fit, say, 300-degree polynomial, and what happens when we do not have a polynomial regression and we have usual linear regression? Okay, this is the kind of graph we get. Same data, same data, and this is the linear regression, meaning the degree is 1. Okay, degree is 1, and this is the double dash is second degree. Okay, and this is 300-degree. Okay, so you can see clearly that this polynomial one, the 300-degree polynomial, is actually trying to fit the noise as well. You can see that it's trying to fit the noise wherever it could. Okay, this is called the overfitting overfitting problem. So it's trying to overfit the data, even though it's just error, it's just noise. Still, it's trying to trying to capture that. Okay, so so and basically the 300-degree polynomial was wiggling around to get as close as possible to the data points or training instances. Right? It is clear that the high degree polynomial regression model is severely overfitting the training data. The linear model is underfitting the training data. You can see that the linear model is basically going through it while the data is like this, right? So it generally, in reality, it becomes really hard to figure out whether your model is overfitting or underfitting or is doing well. And that's interestingly a very common problem with most of the models. Okay, so so how do we find that the model is overfitting or underfitting? One approach is using cross-validation. Remember, in our first session, our model has overfit the data, meaning it has memorized. The other word that we used for overfitting is memorizing. It kind of memorizes entire thing, right? So if something is memorizing, it may fail in the exam on unseen questions, correct? Same is the case with overfitting. So what we do is we use an approach called cross-validation. In cross-validation, we earlier we used cross-validation. We had talked about it. Is that we break down the input data into folds, and we train on we test on one fold and train on remaining folds. Okay. A question from Gopi. In industry, what are the common ranges of degree polynomial that you have encountered? So, to be honest, most of the work that I have done in past, mostly we were able to solve without introducing the polynomial features. Okay, to a very good extent. All right, we did at times. So most of the time it was linear regression with the once in a while introducing the polynomial features, but the outcome wasn't really great mostly. Okay, so okay, maybe I haven't explored too many of such data sets, but in most of the cases, without introducing polynomial features, we were able to get through. Okay, but having said that, if you face a challenge and you're working on say solving it, it's before saying that we are done, you must try with the more polynomial features instead of just useful one. Good question. Now, okay, so here is a very simple way of looking at it. If a model is performing well on training data, but not on the cross validation, right? That means it's overfitting. It memorizes training data and it failed in the exam. That's how you can look at it. So it's overfitting. In this case, the model is too complex. We are taking our model is too complex. It's so complex that it's memorizing entire thing. Now, if a model performs poorly on both training as well as cross validation, that means we need to add more features to it. Okay, more features to it, then the model is so if your model is performing bad in both the cases, training as well as a test, that means it is underfitting. All right. A question from Gopi is, would we ever have to use trigonometric models in real life? Mm, so trigonometric models, you can't say actually. You can't say. That's why whenever you generally get ready with the all kinds of features, you all kinds of situations, and that's all about machine learning. Okay, so yes, actually, interestingly, it's not that uncommon, by the way, to encounter trigonometry. As you will see as we go ahead, right? There will be various functions, various features in the problems that we are coming which are coming up next, that you have to get ready with almost everything. Okay, and that's why this course is actually exhaustive, because we are kind of preparing ourselves for all kind of situations, right? So a question from Noor is more features or more data? Your question is here. Okay. Mm, okay. So a question from Noor is, so if a model performs poorly on both training as well as cross-validation, that means the model is underfitting. In this case, the model is too simple. We might need to introduce the maybe polynomial features and others. Okay, good. So I'm missing the question, Noor. Could you just rephrase it? All right, I'll carry on for now. Okay, I think that slide is coming up next. All right, so I think that slide is coming up next. So here we have polynomial regression, and before that we had, you mean this one? Okay. Question from Gigi is that if the model is underfitting, then do we want to add more features or more data? We would like to add more features, okay, using, say, regression, using polynomial features. All right, wonderful, wonderful set of questions. Let's move on. Now, the other way, one approach is using this thumb rule. Other is looking at the learning curve. What we do is we start with basically, I think we discussed this part. So learning curve are the plots of models performance on the training set and the validation. Okay, so all we do is in case of learning curve that we train our model on different sizes of the data. We keep on increasing the size of data and keep on observing the performance on training and validation set. And once we do that, we would be able to we will be able to see it very clearly. So here, let's take a look at this one. Here, once we plotted the graph, so we got two parts. This is the on the y-axis we have error, and on x-axis we have the training set size. So when we had this much of training set here, it kind of was giving almost zero error, no data, no error. Okay, and as the data grew up, as the training size grew, the error grew. Okay, and initially the validation was too high. Validation error was well, error in the validation set was too low, using the cross validation too high initially. Then the error in the validation became lower, and then it became stagnant. Okay, so here, no matter what we did, the the error in the validation set did not come down, and it kind of became stagnated. So it's an example of underfitting, where your training and validation eventually after a certain size become equal. And also you can see that when you have smaller data set, generally your models kind of overfit. So till this point, it's overfitting because here there is less of error at this point, while less of error in the training set, while in the validation there is actual error. So here it is kind of memorized. If you are asking the questions, when you are asking the questions from the same textbook, which somebody has memorized it, it is giving less error, but something that they have not known, it's giving more error. So that's a scenario with our algorithm as well. So here at till this point, it has kind of till this point, the there is overfitting happening. But after this point, you can see that there is the the error on both sides, as in the validation and training set, is quite high, as it is around 2, and basically this could be a case of this could be a case of underfitting. All right. So at this point in the beginning, it is overfitting, and towards the end, it is underfitting. Okay. All right. A question from Gopi: how come there is no convergence point? Where would you stop training? So it will be very rare to have that situation where it kind of have completely convergence. This is actually equivalent of converging, whereby the difference in validation and training becomes very minor. Okay. A question from Vinta: even the data set is 0, why is RMSI maximum? So here, um, the error on the validation, if let's say there is a one, there is initially there is, I think what we wanted to plot here, maybe let me just think. So if there are, let's say, 2 records on which we are testing, or 1 record we are testing, that's where here it is giving the validation error. So I'm not sure how would you represent 0 number of records in case of training models. So I think a better way would be to take care of I mean, assume it to be more than 0, I mean, very small data set. So here we are saying close to 0%. Okay, this is 80%. So, all right. So this is basically percentages. So it's not, I think it is not number of records. And 0 records is actually not possible to train something on 0 records. Therefore, this data point doesn't make much sense. But here, towards this point, you can see that there is a validation error. Okay. So if you have 2 records, you trained your system using 1 record, and you are validating using another record. And if it just memorized that data point, the chances of error would be really high, or the error size would be really high. Okay, that's what it means. All right, does it make sense to you, Binta? Okay, great. So in the beginning, the validation error is going to be quite high, and as it learns better, the validation error keeps on coming down. All right. Now, so this is the case with while we are considering it to be a single variate linear model, as in the degree as 1, and that's why even though both validation and training are reaching the same point, the truth is that both of them are having equal amount of error. So error RMSE in the case of the root mean square error in case of training as well as testing is quite high. Now, moving ahead. So these learning curves are the example of an underfitting model. Both curves have reached a plateau and they are close and both of them have reached kind of stationary level, and but the error is still quite high. So this is underfitting. So if the model is underfitting, then adding more training data will not help. We'll need to use more complex model. So as you can see that as we are increasing the training set, the validation error remains there. Okay, and therefore adding more data will not help. So this is the point where you would like to increase the degree. You would like to introduce polynomial features and keep on increasing the degree size and see how it is going. Okay, so let's plot the learning curve of 10th degree polynomial model on the same data. Okay, so now here is interesting aspect. So what we did was we in the same problem statement where we had x squared by 2 plus x plus 2, that was our main equation, and now we are fitting a 10th degree polynomial. Okay, so you can see that there is, so what do you conclude here at this point? What's happening here? Overfitting or underfitting? Everyone? At this point, what it has done is it has memorized everything. Therefore, on the training set, the error is quite low. Okay, but on the validation set, the error is really high here. Okay, it's okay. So error is really high. So therefore, at this point, it is overfitting. Okay, when we memorize something, so if the RMSE is low and there is a huge gap between validation and training, the it is a case of um, it is a case of the overfitting. So here there is a huge overfitting, but as we progress, there is still the both graphs are not touching. There is still a huge gap between the two. Okay, there's a huge gap between the two. Therefore, the 10th degree polynomial is kind of overfitting a model. Okay, so again, no matter how much data we are going to use, there is a consistent gap. Consistent gap represents that the model is performing better on training, but not on validation. Okay, all right. So the error on the training data is less than 0.5 RMSE, which is much lower than the linear regression model. Okay, and there's a huge difference. Therefore, there is a overfitting. Even though as the data grows, it kind of seems to go a little slower, I mean, little closer, both of the curves, but still the gap would remain. Okay, so one way to improve an overfitting model is to feed it more training data until the validation error reaches the training data. Okay, so eventually it might converge, all right, on really huge data. I see now, I see. Okay, Okay, okay. So in case of underfitting, if our when we are underfitting, as in our model is underfitting the data, we introduce more features. And in case of overfitting, we either reduce the number of features or decrease the degree of our variable, degree of a model, or we might try increasing the data. Okay. So I think now I got your point, Noor. Thank you. So it might eventually reach. It might eventually learn better if the data is given in a huge size. All right. Now, this is something that we were starting with yesterday. Till here, this is we had talked about. Great, great. So there are a few more. There's a trade-off called bias versus variance. Okay. So a model's generalization error can be expressed as sum of three very different factor errors. Okay, so whenever we are generalizing, as in when we are doing the validation, the result could be a composition of three kinds of error. First is bias, second is variance, and third is irreproducible error. Okay, so the bias error is due to wrong assumptions. The bias error is due to wrong assumption, such as assuming that data is linear when the data is actually quadratic. Okay. A high bias model is most likely to underfit the training data. Okay. So when we have wrong assumptions about the data, we get bias error. Okay. So if we are trying to fit the linear line in a quadratic, then we are going to get the bias error. One example of that is, okay, now while the okay, variance is because of many degree of freedoms. Okay, so when you have high degree polynomial, okay, when you have when you have many polynomial features in your model, the there'll be there will be there will be high variance. Okay, high variance because you have many features to tune and you have many thetas to compute, and there could be there would be overfitting of the training data. Okay, so variance is the result of overfitting, and the bias is the result of underfitting. Okay, so these are the two kinds of errors, and if you try to decrease the bias, the chances of variance going higher is there. So meaning if you try to introduce more features in the model, the chance of getting the overfitting is there. Therefore, we call it bias versus variance trade-off. Okay, right. So you can see that, yeah, that's I think a better way to say it. Thank you, Ross. So underfitting is model is too rigid, as in it has too much of bias, and overfitting is model is too flexible, there is too much of freedom, and hence the variance could be higher. So yeah, that could be another way to keep it in mind. So underfitting is model is too rigid, overfitting is the opposite of it. Good, good. Now, the third part of the errors, the third part that you see in RMSE is the irreproducible error. Okay, what does it mean? This could be the error due to noisiness of the data itself. So remember we introduced the noise ourselves, right? In our data, we introduced the noise. Where did it go? here, right? Here, correct? So we introduced the noise here. This is the noise. So this noise is actually going to be around, say, 25% of our bias C. Okay, this constant that we have here, it is 2, and this could be between 0 to 1, right? Therefore, you can see that this error is actually 25% of our this constant, right? So this is the noise that we have introduced. Okay, no matter what model we fit, we can't eliminate this much of error. If somebody is trying to uh, eliminate this much of error, chances are it's trying to overfit. Okay, this is that. The third part is basically that error. Okay, the error in the data set. Good. All right. So this is the noise in the data itself. The only way to reduce this part of error is to clean up the data, such as we could fix the data sources, we could review if there are sensors broken, or we detect and remove the outliers. Okay. Sometimes when we realize that we are not getting great in the we, we are not our model is not bringing down the RMSE, then what we do is we actually try to see if our data is corrupted, as in are there some records which are outliers and can we remove them, and so on. Okay. As we go ahead, we'll also go through how to remove outliers. Okay. Now, all right. So what we learned is that introducing models complexity increases its variance, reduces this bias, meaning in the other words, it makes it more flexible and reduces the rigidness. And conversely, reducing models complexity, as in reducing the number of features, increases its bias and reduces its variance. Okay, that's why we call it a trade-off. Now, there is something called there's something called regularization. So let's just understand. So what we understood is a good way to reduce overfitting is to regularize the model, constrain it. Okay. A question from Binta is, what does it mean by broken sensors? Broken sensors, as in the data, if the data is coming from IoT devices or sensors or any other data sources, we try to review that. We try to review that. Is there a fault in the way we are receiving data? All right. And if is it because of some wire broken or the sensors broken or some other mechanisms because of which we are getting the corrupted data or we are not getting the proper data. All right. So as we saw earlier, a good way to reduce overfitting is to regularize the model. Okay, constrain it. Okay, it is hard for a model to overfit if it has less degree of freedom. So what we learned earlier was when we put 300 as the 300 as the um, degree, right? So it basically started, it it has just too many degree of freedom, correct? It has too many degrees of freedom. It has too many features and hence too many thetas or too many coefficients which needed to be tuned. So it basically started uh, trying to fit the noise into the data. Okay, and so this is where the idea of constraining comes from. So we reduce the degree of freedom. So one way to do the regularization is just remove some of the features. Okay, decrease the number of features. That's one way. Second way to reduce the degree of freedom is by constraining the constraining the constraining the model by putting a constraints on thetas, saying that they can't go from 0 to that they won't go too higher. If they go too higher, we put a penalty on them. Okay, so 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 it is hard for a model to overfit if it has less degree of freedom. So what is degree of freedom? Degree of freedom is what all can the what all can we change in the model. Okay, is it number of thetas or number of the value of theta? So these are the two things that we can change, right? And that's what it means by degree of freedom. So either we reduce the total number of thetas or we constrain their values that they can't take values beyond certain size. Okay, so that way we could force a model to stay constrained. Okay, so to regularize a polynomial model, reduce the polynomial degree. That is one way of reducing the degree of freedom. Okay, for a linear model, regularization is achieved by constraining the weights of model, weights or thetas, right? That's what we studied. So there are three ways of constraining the weights. Number one is ridge regression, second is lasso, and third is elastic. Elastic is between ridge and lasso. Okay, so if you understand the first one, the rest two you will understand easily. Okay, so I hope everybody got the reason for regularization, right? Okay, let me rephrase what we're trying to do. So when we are trying to fit a model into our data, right? So the model has just too much of degree of freedom. Degree of freedom is uh, how much can the things, how much can the weights move, okay? And how many are the weights? So degree of freedom is a function of how many total weights are there and how much each of the weight can change. Now, if you have more degree of freedom, what it will do is it will start overfitting the data. Okay, if you have just too much of degree, like here in the diagram earlier, right? Since this the next one had just too many of degree of freedom, so it kept on overfitting the data. Okay, so it has too many of the, you can say, curviness, or you can say um, too many degree of freedom. Okay, so yes. All right, so where did it go? All right, good. So a question from Noor is, in linear model, what could be degree of freedom? In linear model, we have weights, right? So linear model is nothing but weight 1 x1 plus weight 2 x2 plus weight 3 x3 and so on, right? So we have those many weights are there. So the number of weights and how much each weight could change, what kind of values can it assume? If it can assume any value, or if the weights can assume any value, what they will do is they will try to overfit. They will try to fit a complex graph on the noise. Okay, That is what it means by degree of freedom. Okay, we'll talk about these things as we go ahead. All right, now before we jump into it, let's just understand what does it mean by L1, L2 norm first. I think this we have done it already. So there are different performance measures. We have already looked into RMSE, root mean square error, as the performance error. Okay. Uh, all right. Good. So before I jump into that, let me answer Noor's question. Question is, like you showed polynomial, do we have a diagram for linear also? So basically, right here, right? So basically, this is the linear one. Okay, since we are talking about only one feature, that's why we have drawn it in 2 dimension. Had it been talking about 2 features, it will be in 2 dimensions and would be there. I mean, this situation there could have been similar. Okay, so this one is the linear, this one is the 300-degree polynomial. Okay, and this is the second-degree polynomial. The curve is second-degree polynomial. Okay, this curve is second. I hope this makes sense to you. Yes, go ahead. Did I understand your question correctly? Yes, this is also an example of degree of freedom of the linear model. So linear model is heavily constrained, and it is basically having only 1 degree of freedom. Yes, thank you, Gopi. Good, great. So, all right. A question from Kamal, is there a clear unit of degree of freedom? So degree of freedom is basically number of weights generally, and but that's not the only degree of freedom. The value of weights, how much they are varying, is also kind of degree of freedom. All right, so we constrain that freedom. So I'm not sure if there is a unit for the degree of freedom, but generally the number of weights is considered as representative. All right. So before jumping into the 3 regularization techniques, we're going to talk about the L1, L2 norms first. So we already know what is root mean square error. Okay. So root mean square error is generally preferred. Perform, perform, Generally, we prefer root mean square error as our performance measure for regression tasks. Okay, because what root mean square error does is it emphasizes the bigger values more than the smaller values. Okay, but in some cases we may want to use another performance measure like mean absolute error. Okay, that's also called average absolute deviation. It's nothing but mod. Okay, so mean absolute error is particularly useful when there are many outliers. Okay, so the this is the formula for the mean absolute error. It's nothing but saying that the overall mean error is equal to summation of all of these values. And what are these values? Summation of the um, summation of what our model is predicting minus what is the actual, the absolute of it. Absolute means if it is negative, convert it into positive. So this value is always going to be positive. So we are summing up from 1 to m1, from 1 to m, and all of such values. So for the first record, whatever is the predicted value of y, we subtract that from the actual value of the first record. Then we do that for all. We compute these deltas for all of the records, and then we sum up all of those and divide by total number of records, total number of training set. Okay, total number of records in the training set. So over the whole training set, this is what we do. Okay, or not only training set, but when we are doing validation also, then also we use the same one. So M here is essentially represents the total number of records. Okay, so if we have many record, what we do is we compute the delta, as in the deviation or the error on each record, convert the negative sign into positive and sum it up. Because if we keep negative sign there, the one negative could cancel the other positive. Even though our model has double error, we end up with zero error. Okay, that's why we have mod. In case of root mean square error, we had a square here. Okay, and square of a negative value is actually a positive value, and hence there we did not need to do mod. So both root mean square error and mean absolute error are ways to measure the distance. Okay, so average absolute deviation and mean absolute error. So are two ways to measure the distance between two vectors. So these are the two ways of measuring the distance between two vectors. Okay, a question from Gopi. What is H again? H for hypothesis. When we this is the our model. H represents our model. X is the actual data record. So when we feed X to our model, whatever prediction we get is this. We are subtracting the actual value of Y from our prediction, and whatever is the value here, we take the absolute of it. If it is negative, we convert it to positive, and so on. Okay. Okay, so these two, there are two ways to measure the distance between the two vectors. Okay, one is called Manhattan and other is called Euclidean. Okay, so 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 Euclidean is nothing but like a Pythagoras theorem. Okay, while Manhattan is like counting the blocks. Okay, so Manhattan distance here, you can see that, let's say we had to go from point A to point B. Okay, so we are computing the distance between A and B. All right, had these been the tip of the vectors, two vectors, these A and B could have been the tip of the two vectors, then 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 we will be basically finding the distance between the two vectors. Now question is that there could be many ways to go from A to B. So here, one way could have been that we could just fly from A to B straight. Okay. Other is go through the lanes. Other is go through the lanes like this. So when we go through the lanes, no matter which lane we go through, which of these three lanes we go through, we're going to end up with the equal number of equal distance. So this, and this, they will have the equal length. Okay, while this one will have a different length. So this one is called Euclidean distance, while these are called Manhattan distance. Manhattan probably because Manhattan has a lot of blocks, and when you have to go from one place to another, you have to go through the lanes, and it has basically the square blocks. So these are basically except for this green one, rest of these are Manhattan distances. And the way you compute the Euclidean is using the Pythagoras theorem. Okay, so x minus x1, this is this distance, and y minus y1, this is this distance, and we square the two and sum it up. That is the Euclidean distance. While Manhattan distance is simply counting the absolute value, y minus y1 plus x minus x1. That's all. So whether you go this way, or you go this way, you're always going to get the Manhattan distance. So L1 norm is essentially Manhattan norm, because there we are essentially computing the summation of the values instead of squaring them. Okay, so computing the sum of the absolute corresponds to L1 norm. It is always denoted by vertical lines. Okay, vertical lines, and it's also called Manhattan norm. While L2 norm is basically the root mean square error. Okay, we basically compute the root of sum of squares and divide by the total number, and or I mean, even if you don't divide that, mean square error, the uh, okay, so, and that's called L2 norm. Okay, L2 norm is denoted by double, here the L1 was represented as double lines and followed by one s suffix, and here it is double lines with two s suffix. It's also called Euclidean norm. Okay, LK norm, the LK norm is generalization of the two. So in case of LK, what we do is we compute the mod of each error and raise it to the power of k and sum it up, and then do the one, raise the whole sum by 1 by k. Okay, so this is the LK norm. LK, it's basically a generalization. We do not use it much. We either use the absolute or the root mean error. Okay, so L naught means it just this is this is one, this is one, this is one, and so on. So it will give you the cardinality of the vector, and L infinite just gives the absolute maximum value in the vector. So this is LK. The higher the norm index, the more it will focus on the larger values. Okay, and it will, cardinality means size. Okay, okay. K is any number actually. When we say L3, L3 would be L3 would be V naught absolute to the power 3 plus V1 absolute to the power 3, and so on, and then 1 by 3. So that's what K refers. K is basically generalization. K is basically generalization of the same idea. Now, so as we increase K, meaning we increase the norm index, okay, and it will start focusing on more and more on larger values than the smaller values. So it will keep on neglecting the smaller values. So because it's the 1 cube is actually 1, while 2 cube is actually 8, and 3 cube is 27. So you can see that 3's cube, the result of 3's cube actually over I mean, mm, hides or over what should I say? So the result of 3 cube is actually making the significance of 1 cube and 2 cubes lesser, right? Therefore, generally, as you increase k, the it will more and more focus on the larger values than the smaller values. It exaggerates, it more and more exaggerates error. This is why the root mean square error is more sensitive to outliers than the MAE. Okay, so so k equals 2 is more sensitive to outliers than k equals 1. But when outliers are exponentially rare, like in a bell-shaped curve, the root mean square error performs very well and is generally preferred. Okay, so we generally prefer root mean square error for the same reason. One, it does the it removes the negative sign. Second, it basically emphasizes the outlier more. Okay. Okay. A question from Noor. Any example when we use MA? We'll be using that in Lasso as we go ahead. Okay. So whenever when okay. So we'll talk about that MA again after. Okay. So we'll come back to this slide after we have finished the rest. This is something that would mean more when we finish the rest. Okay. Now let's understand these regularization techniques called ridge, lasso, and elastic net. Okay. So a question from Binta is, if k is 0 and in infinite, what is the result? It has got infinite cardinality. Okay, because k0 means it's basically summation, infinite summation of 1. Okay, so that's what it is. All right. Good, good. All right. So basically, what ridge regression does is it regularizes the linear regression. It's a regularized version of linear regression. So what we do is we add a regularization term to the overall cost function. Okay, so we add this term, meaning with respect to all of the thetas, what we do is we compute their squares and sum up all the thetas and add this. Meaning, if we are going to increase thetas, the error is going to grow. Okay, therefore, we are forced to keep thetas as small as possible. Okay, so adding so so the cost of the cost function, whatever the cost function was basically the value predicted by our model minus the actual value, square of it, and summation. We are adding this term to it, meaning we are forcing our model to keep thetas small. Okay, so we are adding this to our error. So if we have bigger value of thetas, the loss is going to be bigger, and hence our gradient descent or any other algorithm is going to make sure that thetas are smaller. Okay, so this is ridge regression. In ridge regression, we essentially force the weights to stay small, and we do it mathematically by introducing this particular term. Okay, so adding a regularization term to the cost function forces the learning algorithm to not only fit the data but also keep the model weights as small as possible. Okay, so when model weights are smaller, what happens is the contribution, the individual contribution of the various features is capped lower. Okay, if you have really high weights, if okay, so here there is a term called alpha. Alpha is that regularization parameter. So more is the alpha, smaller are going to be, the more is the alpha, smaller is going to be the impact of the actual features. Okay, so so keep in mind that this term regularization is only used in the cost function. during the training, not during the validation. Once the model is trained, we evaluate model's performance using the unregularized performance measure. Okay, so this is only used in case of training where we are computing the weights. Okay, so once the weights are computed, we do not use the regularization term. All right. So how is the value of alpha determined? The value of alpha is determined. Basically, that's a what do you say? It's a hyperparameter, and there is no straight away method of alpha. So we'll talk about how does the overall outcome varies with alpha. Okay. So a question to all of you is, why add regularization term only during the training, not while evaluating the model's performance during testing? Anybody? Correct. So correct. So the weights are being adjusted at the time of training. So regularization term is for forcing the weights to have lesser degree of freedom while computing the weights only, not while using the weights. Therefore, we only use the regularization term only during training. Okay, so cost function should have optimization friendly weights during training, while the performance measure used for testing should be as close as possible to the final objective. This is why we evaluate models performance using the unregularized performance measure. Okay, so if you take a look at the error, okay, or the cost function, this is our cost function. Okay, so this is our cost function. I did not get your question, Binta. A question from Gopi. So if it is during training, is this a form of normalization like softmax normalization? So it's basically a kind of normalization. Basically, what we are trying to do is we are forcing the model to have the smaller weights. Okay, we are forcing the model to have smaller weights. Okay, and a further question from Kamal is, I'm not very clear why we are doing regularization. Is it to avoid overfitting? Yes, this is to avoid overfitting. So the more degree of freedom, as in more number of weights we have, or the more each weight could vary, the more each weight could vary, the more it would overfit the data. Therefore, what we are doing is, instead of decreasing the number of parameters, number of features, we are forcing each of the weights to be as small as possible. Okay, so that's what we are doing. A question from Kamal is, regularizing to not use too many variables or too high degree of polymers makes sense, but why forcing the weights to be small? Good question. Okay. So, all right, let me try to answer this. So we generally do not know out of the, let's say we have a set of features and we are training it, and we generally do not know which of these polynomial degrees, which of the features we can remove, right? So it's easy to say that we can have it's easy to say that we can have lesser number of features, lesser number of weights, right? But we do not really know in practicality, in practical, that which features we can do away with, right? So removing the features or decreasing the number of weights would would be impractical, right? So instead of that, what we do is we constrain the weights so that so that so that the features whose weight, whose significance is lesser, would be kind of eliminated. The weight of that one will become zero. So, so we are forcing the weights to stay smaller so that the significance of various features would keep on kind of forced down, meaning if the weights of some of them are put to zero, then those features will be automatically removed. So by introducing a regularization term, we are forcing the weights for some of the features to become zero. Okay, we are forcing the weights for some of the features to become zero and or become really small. And therefore we are trying to regularize or control the degree of freedom. Okay, it's a very good question, Kamal. So was I able to answer? Okay, all right. So Kamal's point is that, but if none of them become zero, then it it is not of that much help. Correct, correct. That's why that's why the tendency is to have this regularization term and tweak the alpha accordingly. Okay, okay, all right. Yes. A question from Pavan is how we are reducing the weights in this expression. Okay, so thetas are our weights, by the way. So this is our error function or cost function. Objective is to keep the cost function as low as possible. Correct? Now, if thetas are bigger, the cost function is going to have a bigger output, correct? Because we have added an extra term. This is anyway this is a function of the mean square error and the function of our the what do you say, the feature values, right? Now here, since we have added one more term, what's happening is the moment our thetas start becoming bigger, the cost function starts becoming bigger, right? And hence, thetas are, we'll have our gradient descent will keep on choosing thetas which are smaller and smaller so that the error remains smaller. Okay, that's how we are reducing the weight in the expression. So we are assuming that our gradient descent is going to minimize cost function. So we have added an extra penalty to it. We've added an extra penalty to it with respect to this thetas. Okay, so that if the moment it goes keep puts one theta really high, this term will go really high. Okay, and hence it'll say that no, we have to bring it back, and it goes in the opposite direction and will reduce the thetas. That's how it is going to, it's going to force that thetas to be 0. So this is the total cost, and the total cost is the standard, the mean square error, plus this extra weight. Okay, this is something we are trying to reduce. So the moment theta start going up, the overall cost goes up, and if theta goes down, the overall cost goes down. Wonderful, wonderful set of questions, and yes, I'm sure that this discussion would help all of us. Okay. Yes, alpha is a positive number. Thank you. So that's something that we have missed out here. Okay. Question from Pawan further is, why theta square? Why can't it be, say, mod and summation of the mods, correct? One is square is used to make negative positive. Second is to emphasize on bigger thetas more than the lesser thetas. Okay, so the moment one of them goes really high, we get the heavy cost. So it doesn't let either of the thetas go outliers. Okay, that's the one of the ideas behind square. But having said that, the lasso regression is same as this one, except for here, instead of theta square, it's mod of thetas. Okay, so both have its positives and negatives. Okay, so now we got how many? One more regularization, one more hyperparameter called alpha. Okay. That's correct, Kamal. Your understanding is right. Instead of making the not so important disappear, it will try to make the bigger one smaller. That's correct. That's exactly the the idea behind ridge regression. The other one, which one reduces the individual to 0, is the lasso one. Okay. Okay. So okay. So in many cases, we so again, one of the objectives is to reduce the significance of reduce the significance of the features which have more randomness in it. So making them disappear is just in some of the cases, but overall agenda is the features which have more noise should pay less contribution. Okay, that's the sole idea. So the features which have more noise should pay less contribution in terms of the model. Okay, instead of making them completely disappear. Okay, so we not only constrain the degree of freedom by cutting down on weights, but also bringing the significance of individual feature lesser. Okay, by keeping the weights in control. All right. So both have their advantages. We'll come back to that again. Okay. So regularization helps us to fix overfitting. For underfitting, we'll have to introduce more features, and when we introduce more features, it will start to overfit, and that point of time we will need these regularization. All right. So okay, did I miss any question? A question from Noor is, so it means that if two features have good correlation, then we would keep its weight high if two features have a good correlation, then we would keep its weights high, and if there is no correlation, then we will keep it low. Correct. We generally, it's a hyperparameter. Alpha is generally hyperparameter, so there is no direct way of doing that. It's basically just the way we used a hidden trial method like grid search in order to do the alpha. In order to find the other hyperparameters, alpha is similar. Okay, wonderful, wonderful set of questions. Yes, penalizing. I'm just reading the questions. Penalizing large weights will prevent you overfit the noise. That's exactly right. Thank you, Ross. All right, good, good. Now, this was our small discussion on the ridge regression. So basically, if alpha equals 0, then it's equivalent to the normal linear regression, right? If alpha is 0, then this term disappears, and the ridge regression is nothing but usual regression, usual linear regression. And if alpha is like 50, if alpha is like 50 or really huge, what would happen is this term will play such a significant role that the line will be completely horizontal. Okay, the model will be completely horizontal. It will reduce the significance of all of the features. Okay, so note that the bias term theta naught is not regularized as the sum starts at I equals 1, not 0. Okay, so you can see that the theta 0, the bias, is not something that we are regularizing here. Okay, except for because theta naught is not forcing, is not coming with any of the features, right? It's kind of an independent one. Therefore, we do not regularize the theta naught. Okay, we are just constraining the weights of the features, and hence bias term is not required. Okay, so if W is the feature vector weights, let's say if W is the vector of feature weights from theta 1 to theta n, then the regularization term would be equal to 1 by 2 the mod of the L2 of W square. Okay, so this is what it is. So this is L2. L2 has a square root, therefore we are squaring it and putting 1 by 2 in front of it. Okay, now, so one more thing that we must do before applying any kind of ridge regression or anything is use scale the data so that all the features values are between 0 and 1. Okay, and before performing the ridge regression, we must do something like standard scaler. Okay, otherwise instead of weights controlling the variance of individual feature or individual noise, the weights will end up being based on the actual value. So instead of keeping the absolute values of each features, we must scale them before applying ridge regression. I hope this is clear to everyone. All right. So let's train the model using ridge regression on some linear data using different alpha values. Okay. The code is not really important right now. The important idea here is that we understand this because okay, because here all of these algorithms are readily available to you. Okay, so here what you see is Let me also keep it ready. Okay. Yeah. So what we see here is that if, okay, if alpha is zero, it'll be like a usual linear regression. There is nothing much to it. But the moment we increase alpha to say 10, what happens is that it starts to it starts to come back to kind of the horizontal line. So if alpha is 100, it's only the horizontal line because it does not, if alpha is 100, it will only play around with various values of theta to decrease. It is equivalent of saying that this term is completely zero. If you put this at zero and this is the only one that's playing the role, then what will happen is here the values of thetas would be something that just minimize between 0 to 1, and that is something okay. So the model that gets generated will completely ignore the features. Okay, this one is completely ignoring the features, meaning no matter what is the value of x, the value of y is fixed. Okay, so the significance of the features keep on going down if we keep on increasing the coefficient of the ridge regression, this the alpha. Okay, what do you call this? Okay, it's basically a hyperparameter alpha. Okay, so as alpha grows, the it keeps on kind of reducing the significance of individual data points. So no matter what we have as x, the value of y is kind of independent of x. There's only slight impact. Here there is a little bit more impact when alpha was 10. It is kind of having more impact, but the maximum impact of value of x on y was here. Okay, so you can see that as the ridge regression coefficient grows, or the term, uh, we keep on increasing the term, then the significance of individual feature becomes significance of individual features become lower and lower. Okay. Okay. So a question from Binta is that is ridge regression still linear? Yes, it's basically a linear regression. It's basically improvement to linear regression, and it only adjusts the value of slope. Yes, it only adjusts the values of various slopes. It doesn't change the bias, as in it doesn't change the distance from the center of the actual model. Okay, so the C remains as such, and it just tweaks the slopes. All right, so the same thing, if we were talking about, say, situation where our model was fitting like this, okay, when alpha was 0, this is how it looked like. And the moment we have a tiny alpha, what will happen is it'll kind of bring it down. It'll make it less curvy, okay? And then when alpha is 1, what happens is it kind of becomes very, very straight line. So the significance of changing of x1 was higher in case of alpha is 0. You can see that as we are changing x, this is value of y is changing really fast, right? When in this case, the value is changing a little bit slowly. right? As we are changing x. So that is the significance of introducing the ridge regression. All right. So let's take a break and for 10 minutes. Okay, so break for 10 minutes. 10 minutes. Hi everyone, I'm back. So should we start now? Hi everyone, should we start? Okay, so I'm just trying to see if my notebook is running. All right, so here the data is first expanded to include the 10 degrees, okay, 10 polynomial features with degree as 10, and then data is scaled using a standard scaler, and then finally ridge models are applied for the resulting features. Okay, is it stuck somewhere? What's with this? Okay, let me just see what's happening here. Let me just open a terminal and yes, Gopi, you wanted to say something? All right. What's with this? So here, I think there is a mistake in this. Anyway, I'll just skip this part and move on. Okay, so looks like the newer version doesn't look good. Okay, so for now I've just checked out an old version. So I'll open this as well. So I think we were trying to modify the notebook recently, and because of which some of the changes have gone a bit different. This is where we are. This is where we are. So what we're going to do is we are going to run all above. All right. So by the time that happens, let me just walk you through this. All right. Looks like this. Oh, again, the mute button pressed. So, okay. All right. Sorry about that. So what we have done here is, let me just increase the font and explain to you. So we have just created a class called plot model. And this plot model does multiple things. Number one, it first of all creates a model, this is the model, then adds this to the pipeline. This is where it's adding it to the pipeline. Okay. And the way it's basically adding the polynomial feature, then adding a scalar, standard scalar, and then doing the regularization. In few cases, when the polynomial is passed as false, it it doesn't do this. Okay. It doesn't do the pipeline. Otherwise, it does the pipeline. Okay. So using this pipeline, it first adds the polynomial features, then does the standard scaling, and then here is the actual model. This is where the model happens. So fit method is valid for this as well as this. Okay. So essentially this plot model, what it does is, given multiple alphas and given the model class, it'll basically plot this graph. And what is this graph? This graph is basically, given the value of x, what is the value of y that is being actual versus predicted. Okay, that's what it is. So these ones are with the predicted ones, while these dots outside represent the actual values of y. Okay, so here that's what it does. It is basically fitting a high degree of a polynomial at this point. Okay, and yes, let me just go up and so in here, it's without any features or scaling. This is what is happening in case of a linear one. While in this case, it's basically doing the adding 10 polynomial features, 10-degree polynomial features, and then for various alphas, this is the chart. Okay. Okay. So basically the and you might be wondering that who is adding the the term. So you can take a look at this. Here we are adding the polynomial features, and before that we have a model class, and we have whatever arguments we are passing to this plot model, we are passing those arguments to the model class method. So here we are when we are calling this function, we are also passing this. Okay. Uh, After alphas, we are passing the random state. Okay. All right. So, yep. So here in the model class, whatever is the model class that we're passing, we are saying that, say we are saying ridge, so we are instantiating ridge with the given alpha for each of the alphas, and so this model class ridge takes alpha as the first argument, and rest of the model arguments here. Okay, so random state equals 2 is passed here. So we're passing, so here, this is where we are training our ridge regression. Okay, so this is the model class, and then we are creating the pipeline, adding this here after the standard scalar, and that's all. Okay, so that's what is happening. Yeah, model class is a function argument. So it's not really using 3 alphas at once. I'll show you. So we are passing 3 alphas, right? So what it is doing is, first of all, it's zipping alphas with the colors. Okay, alphas with the colors. So we get a tuple. We get a tuple after this, correct? So, and once we get that, we iterate over the list of tuples. We iterate over the list of tuples. So this piece of code is being called for one alpha at a time. Okay. So we're going to, first of all, create the model using the model class. If it's a polynomial, then we are basically creating a pipeline using polynomial features first, then standard scalar, and then the actual model here. Okay. And then we are saying model.fit. Good. So this is what we are doing. So for each of the values here, earlier we passed polynomial as false, and second we passed the polynomial as true. That means this one is without any polynomial features, and this is basically a straight line fitting. And here the polynomial features are 10, as you can see here. So degree is 10. So polynomial features are going to be, I think, 10, 10, 10 only, right? Because it's a linear one. Okay, and that's pretty much. And which data are we fitting? Here we are fitting our standard x and y. Our x is this. Our x is this, which is sorry. Our y is this, which is a linear line plus some random noise, and we are trying to fit various models to it. So our data is basically generated using a linear line, as in the single line with some noise. And when we have when we have uh, when we have alpha at 0 on this side, this is how it looks. So it's basically doing the curve fitting on the random data, right? When the alpha is really small, okay, when the alpha is really small, something like this, okay, which is it's basically doing the curve fitting, but it's kind of more flattened out. If alpha is 1, that means alpha is really big. Then it's kind of a straight line. You can see that it's kind of a straight line. Only towards the end, it is going up. Okay. A question from Gopi. Why include bias? Where are we? So this is our model class. Yeah. So while including the polynomial features, we want to add polynomial features with respect to the with yeah. I think polynomial features also have a way to include a bias constant with it. Okay, a constant bias with every degree. So that's what I think. That's what it is. Include bias means. All right. So this is what we are basically doing. So you can see the impact of alpha on the graph. So when alpha becomes higher, it is kind of straight line. Okay. When alpha is lower, it's kind of very curvy. So it's trying to overfit the data when the alpha is lower. Okay. So that's the sole idea behind ridge regression. All right. So polynomial regression with ridge regularization, increasing alpha leads to flatter, less extreme, more reasonable predictions. This reduces the model's variance but increases its bias. Okay, just like linear regression, we can compute the ridge regression by either using the closed form equation or normal equation or by performing gradient descent. Okay, so if we had to implement this by ourselves, we will introduce one term here at this point, alpha a, in the equation, and this will be basically the ridge regression term. Okay, this is going to be an n by n matrix. an identity matrix, just that the left top corner is going to be 0 because we don't want to include the bias term. Okay, so essentially this is xt.x, right, which is containing our features, and we would like to add um, add add uh, certain amount of weights or certain amount of thetas to it. So I think, let me just think over it. So yeah, so basically, if you try to implement the ridge regression using closed form, this is the kind of equation that would come. Okay. Okay. A question from Gopi: why did we make the include bias as false in our polynomial features? Because the bias term was already there. Bias term was already there, so we did not need bias term. Probably that's one of the reasons why we have used include bias as false. Okay. All right. So this is how it is. So the identity matrix means a matrix which has all the values on diagonal as 1. So here A is an identity matrix. Okay. Except for this corner. This corner is 0. Okay. So this is how it looks like. And implementing it is quite simple. And okay, so if you really want to use the closed form equation, the normal equation, we could simply say ridge alpha equals 1, solver as Cholesky, and that would fit the data. Okay, so remember, if you are using this particular solver, that means we want to use the normal or closed form equation. All right. And if we want to do the computation of ridge regression using stochastic gradient descent, we could simply say SGD regressor. Okay, here we are saying ridge along with the solver at Cholesky, and here we are saying use the SGD regressor along with penalty as L2. Okay, penalty as L2. I think that answers your previous question. And yeah, so the regularization term is called penalty. We earlier confused it with the loss. Okay, until we saw the documentation. So yeah. So all we do is, in case we want to solve it using SGD regressor, the stochastic gradient descent, then we can use the penalty as L2. L2 means the regularization term is going to be squared. Okay. So penalty hyperparameter sets the type of regularization term to use. Okay. And it is specify L2. L2 means we want SGD to add a regularization term to the cost function. It is equal to half of the square of L2 norm of the weight vector. Okay. All right. A question from Gopi is, what is solver doing? Solver is basically a particular algorithm here in case of ridge. Okay. So that's what is solver. Now, all right. So this is how you can compute the ridge regression. So let's take a look. So this is the example here. So we are trying to predict the value of y given value of x. Okay. So this is the value, and what was the x and y? So 1 plus 0.5x, right? 1 plus 0.5x. Okay. So 1 plus 0.5x is 15 into 1. Okay. So 1 plus 0.5x is 15 into 0.5 is 0.75. 1.75 it was supposed to be the actual answer. Okay, but here it is 1.55. Okay, so there's a mistake of 0.2. This okay. Now, if you want to solve it using the SGD regressor with the penalty as 2, so this is what we get. So we get a value of this. Okay. Okay. All right. So okay. So that's what we are trying to do there. Now, all right. Now, a question from Kamal is in HDD regressor, the penalty is L2 and random state is 42. We did not set alpha there. Yeah, so we let it assume. And that's what I think this is also saying, that a lot of parameters it is assuming. Let's just see if it provides us a way to. Okay, so penalty is L2. This is okay. And you can see that alpha, okay, it defaults to 0.001. All right. Good question, Kamal. So yes. All right. Next question is from Gopi. So there are variants of ridge regression by changing solver. So there are variants of ridge regression by changing solver. Yes, there should be. So one is SAG. There are a couple of okay, more. So I'll just show you some of them. Okay, so here what we have is, one is we can specify alpha. Okay, and that's okay. Then max iteration, precision, and solver, right? Okay, so chooses the solver automatically if you say auto, and then SVD and this. Okay, so Cholesky basically uses the clause form equation. Okay, and we have SAG, which is stochastic average gradient descent. All right, so we could use, so this is another way of using stochastic. So this one was using the SGD regression, like stochastic gradient, and there is a variant of it using average gradient descent. All right. So this one, the Cholesky one, is the one which is uses the normal equation. All right. So now let's move on to the next topic called Lasso regression. Okay. Basically, it's a Lasso regularization technique on top of our linear regression. Okay. So Lasso regression is least absolute. Basically, it's least absolute shrinkage and selection operator regression. Okay. LASSO. Least absolute shrinkage and selection operator regression. Okay, that's what is Lasso. Like ridge regression, a regularization term is added to the cost function, but it uses L1 instead of L2. Okay, so instead of squaring it, it just uses the mod of it or absolute value of it. Okay, so this is what the cost function looks like. Okay, so we can simply use the same method, plot model, if we pass the lasso here, and we have imported lasso from linear models in sklearn. So this method basically takes this plot model basically takes this as the argument, and it calls this lasso with alpha and remaining arguments with alpha. So it's going to call lasso with 0, then 0.1, then 1. So that's what it's going to do. And in the case of polynomial, what it is going to do is it's going to call lasso with 0 and in the pipeline by adding say 10 features to it. Okay, 10 degrees of polynomial features to it. Okay, so that's what it is going to do, and this is how it looks like. Okay, so the important part here is that we need to compare this and the above one. Okay, so this one is okay, which we have already seen. There is not too much of a difference this side. While on the right hand side here, you can see that this line is more like a straight line, more like a straight line. Okay, a question is what is tall? Tall stands for tolerance. This tolerance is we are passing to lasso. Okay, that's what we're doing. Okay, a question from Noor. Alpha values are different for linear if we compare. So in both the cases, we are passing the same alpha value. This is what we did earlier also, and this is what we did here. Okay. Alpha values are different for linear. Okay. So I don't get the question. So do you mean that we are using the alpha value for linear when we are saying polynomial false, we are passing different? So it is different. So when we are passing polynomial true, then we are okay. So what we have done is same data on both the sides. This one with absolutely the basic linear regression. This one is with polynomial features. Okay. 10 degree of polynomial features. This one has these three lines are for alpha 0, alpha 1, alpha 0.1, and this one is for alpha 0 and alpha 10 to the power minus 7 and alpha 1. And here we did 0.5, minus 0.5, minus 5, 10 to the power minus 5. So here 0.7, minus 7 and there minus 5. So yes. All right. Okay. All right. So what are our observations? Okay. So this left one is the plain linear regression, while the right one is the polynomial. And so an important characteristic you will notice in case of lasso regression is it completely eliminates the weight of least important features. Okay, it sets them to 0, right? So Kamal, you remember the discussion we had? So basically, lasso is the one that makes sure that remove the it'll remove the uh, unnecessary noise. In the previous case, even when the alpha was 10 to the power minus 5, even then it was kind of coming like a curvy one. Okay, and here, even when the alpha was smaller, still it cut down the noise. It cut down the noise due to in the data. Okay, in the data. So you can see that using the lasso regression term, even when the alpha was really smaller, it actually regularized our our graph. Okay, so basically lasso regression automatically performs the feature selection and outputs the sparse model. Okay, the model with few non-zero feature weights. Okay, The dashed green line that you see here is the right plot. Looks quadratic, almost linear. All of the weights of high degree polynomial features are equal to 0. Okay, so that's what it has done. Okay, so it has this what it has computed. All right. Now, the third model, should we move or do you have more questions with respect to it? Yes? Yes? Yeah, that's correct. That's correct. The here you're right. So here what you see here is it's essentially 10 to the power minus 7. Okay? So if you see this, basically, okay. So it's like saying 2 to the power 4. All right? Great. So you're right. Question is why not use exp? Actually, the to the power is quite easy. Okay. Otherwise, we'll have to use math dot something. Okay. So this I think this would be calling the same math operator internally. So asterisk is provided by Python by default, so we use that one generally. Okay. All right. So yes. So question from Kamal is I'm not still clear with the use of ridge regression. Okay. And lasso still makes sense. So essentially, we are assuming in case of ridge regression that there is a noise in each of the features. Okay, each of the features contain noise, and therefore the ones that contains noise should not matter much, and therefore their weights need to be reduced down. That was the idea in ridge regression. Well, in case of lasso, we are saying that some of the features are irrelevant and therefore their weights need to be turned to 0. Okay, that's what is actually happening as a result of this mechanics. Okay, so basically, since both ridge and lasso have their own pros and cons, so we use a combination of both in the real scenarios. A question from Noor. The model looks good even when we are not using ridge or lasso in this example. Why are we using it? Okay, so in this example, we were able to achieve it to a very good extent. So we don't really need it upfront because here we know the reality. But in when we don't know the reality of the data, since here we know that our data is in the form of a line, right? Okay, in the form of a line. Therefore, we feel that there is no need. But in case of real life, what if your model is overfitting the data? If your model is overfitting the data, we might have to use a combination of ridge and lasso regression. Okay, a question from Bintao. What can we do with the results of the predictions of ridge, lasso, and elastic nets? Okay, so basically the result of all these three is a linear regression model on your data. Okay, that's the objective of all the three. Okay, all right. So a question from Kamal is, can you give an example where lasso totally fails and we need to use ridge regression? Okay, and I think a better way would be that if we had an equation with x1, x2, and there are two variables instead of one. There are two variables instead of one, and one of them is having a lot of noise, and there is another one which is having no noise at all. So lasso will eliminate the one that was having more noise, while ridge will maintain both the variables, as in both the features, and the it won't set the weight of the feature which is having more noise to 0. Okay, so that's where the ridge will work, while lasso will work in the case when we are thinking that some of the features are not relevant. Okay, so I hope that answers the question. Okay, so if we take an example, let me take a step back and try to answer that. So lasso is great when we want to just eliminate some of the features, while ridge is great when we want to eliminate the noise in some of the features. Okay, the ridge does not eliminate ridge does not eliminate the features that are irrelevant, while lasso does not lasso only keeps the features which are the most relevant. Okay, therefore we can't use both of them. We can't use either of them. Instead, we use we use a combination of them, and the combination of the two is called elastic net. It's a middle ground between the two. Okay. A question from Kamal is, so the noise in a feature is like one of the sensors is sometimes not working but must be considered. That's right. That's right. So, all right. All right. So there are quite a few hyperparameters here. Okay. Our weights or the parameters are on one end, the thetas. Okay. Other than that, we have learning rate, we have learning rate, we have the initial value of thetas, and we have quite a few other terms that we discussed earlier. Then other than that, we get few more terms, alphas and then R. Okay, so elastic net is the middle ground or a composition of the two. It's ridge and lasso. Okay, the regularization term is a simply mix of both ridge and lasso regularization term. We just put one more coefficient here, R, and 1 minus R. Okay, if R is 1, then this will be 0, and therefore it'll behave like lasso. If R is 0, then is going to be 0, and this will behave like a ridge. Okay, so if R is 0, the elastic net behaves like ridge, and if R is 1, it behaves like lasso. All right, so question is, when should we use linear regression? Ridge, lasso, or elastic? Okay, elastic net. All right. So first of all, let's understand that we should avoid plain linear regression. Always preferable to have at least a little bit of regularization. Okay. In the real world, linear regression is not going to solve because there are chances of a lot of noise and overfitting. Okay, so ridge is a good default, but if we think only few features are useful, we should prefer lasso, or we should just use the elastic net, as they reduce the useless features weights down to 0. Okay, so in general, elastic net is preferred over lasso, and since lasso may behave erratically when number of features is greater than number of training instances, or when several features are strongly correlated. Okay, so I think this answers your question, Kamal, further. So if the lasso may behave erratically if number of features is greater than number of training instances, or when the several features are strongly correlated. Okay, so if many features are strongly correlated, it could behave in a very wrong way and might eliminate some of the features. Okay, that's right, Gopi. The way we decide the value of R is experimenting different values. Okay, so that becomes a hyperparameter. All right, so let's try to implement ElasticNet. ElasticNet is again part of linear model package, and we can import ElasticNet. And all we need to do is call ElasticNet with a value of alpha and the L1 and L2. Okay, this is the R. L1 underscore ratio is that R value. Okay, now we are saying ElasticNet.fit, and we're passing the data and we're predicting the value. You can see that the value is 1.54, which is good enough. So we are saying 50-50 of regression and 50-50 of ridge and lasso. All right, that's what we are saying here. All right. So this is another L1 ratio is another hyperparameter. A question from Kamal: number of features is greater than number of training instances. Can that ever be? My understanding was that later should be manifold than the former. Okay. So yes, that's a very, very rare case. And in that rare case, lasso might behave erratically. Okay. A question from Binta is, what can we do with the results of prediction from ridge, lasso, and elastic net? Okay. So basically, all we are trying to do is we are trying to do a regression, meaning we are trying to do supervised learning. Okay. And it's a regression task. So whenever we want to predict a value, whenever we want to predict a value, we can use the we can use the these regressions. Okay. All right. Am I understanding the question right? So the objective of either three of these is to make our linear regression better. Okay. That's what it is. Yes, Binta, was I able to answer your question? You can feel free to unmute and ask, or you can just type again. Okay. Question is, what does mean of their input? Okay, so let me show you what we have done here. All right, so what we're trying to do is we have a line. Okay, we created this data X and Y. Okay, this is the data that we created. Ideally, you will get this data. Ideally, you will get this data as the from your problem statement. Okay. Now, using the regression, what we have done is we have figured out a model. Here we know the model. We have figured out the model, and then we are trying to predict the value of Y given the value of X. Okay. So that's the objective of regression exercise. Given a training set, be able to predict Y based on various values of X. All right. So we can use the same weights, same model, whatever we have used in training, we can do the fit. Okay. We can do the prediction. All right. We could use a function called predict in order to predict the value once we have trained using Ridge, Lasso, or Elastic Net. Correct. Yes, that's right, Vinta. So we could say Lasso regression dot predict or Elastic Net dot predict and so on. All right. Was he able to answer? Okay. Yeah. So let me rephrase. Let me reread your question. Probably I misunderstood the question. Question is, what can we do with the results of prediction from Ridge, Lasso, and Elastic Net? So when we are doing the prediction, meaning we are doing the fit here. Okay. So this Lasso regression has developed the various weights and coefficients, right? So it has developed the various weights and coefficients, correct? So I'm going to just say this intercept, okay? And you can see that intercept. Okay, so we have this is the coefficient and this is the intercept that is generated. Now, at any point of time, if we have a lot of values to predict, okay, so we have trained our model. Now we can utilize that in the production environment and use this model, which we have trained using Lasso or any other technique, to the further prediction of the values. Okay, was I able to understand your question? That's right, Pinta. So the input is 1.5, that's right, and the outcome is 1.537. Okay, so so Lasso has understood the model and now it's predicting the values of Y. Okay, all right, good, good. All right, great, great. All right, good question. Now moving ahead. Okay, there was a question from Kamal that if the number is there can there be a scenario where the number of features is greater than training instances? So it's very rare, but it could be possible. If you have, let's say, image, let's say we have an image of 1024 by 786 pixels, then the total number of features could be more than the total number of record training sets available to us. So that's just very rare, okay, but it could be possible. So Lasso may behave erratically in one scenario to another scenario when the features are strongly correlated with each other. So in those cases also, Lasso may not work very well. Okay. A question is, in the case where there are so many features, is it possible to even predict? So yes. So in that case, question is, if the training instances are lesser than the total number of features, is it even possible to predict? All right. Yes, that's right. It may not be able to predict very clearly, but it should be able to give you some kind of a result. Okay. It won't be very powerful, but it should be able to predict. Okay. A question from Noor: what is the performance measure to know what values of R or alpha is good? Okay. Again, it'll be basically based on cross-validation, and R and alpha could be computed as the hyperparameters using the same validation techniques. All right. Yes. So Kamal's question is, when you don't have sufficient training instances, then you should better get the training instances instead of trying to use so many features. So, right, right. But sometimes it could be the case. I'm not able to visualize what could be the case where number of features are more than the training instances, but maybe there could be a case. All right. So your point is very valid. So, all right. So this way we could actually use elastic net to do the prediction. And the next mechanism of early stopping is the next mechanism for regularization is early stopping. Okay, so what one is one we found the regularization as a good technique. The other one could be using early stopping mechanism. Okay, one was by introducing coefficients like a ridge lasso or elastic net. The other could be early stopping. Okay, so remember our discussion with respect to SGD, where we actually stopped before, right? Same like interrupt, that's right. So a different way to regularize iterative learning algorithms, such as gradient descent, is to stop training as soon as the validation error reaches the minimum. This is called early stopping. Okay, so I see. Okay. All right. Good. Good. So that's what Gopi meant earlier by convergence point. Oh, when we were discussing about the two graphs, right? The cross validation one and the training one, right? So they basically converge. Okay. Great. Great. So 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 what happens is, let's take a look at this. As the number of iterations, the x-axis is number of iterations. X-axis is number of iterations, and y-axis is root mean square error. And the blue one corresponds to the validation set, and dashed one is corresponding to the training set. So, okay, so as number of iterations go higher, the the difference between the root mean square error keeps on increasing. Okay, initially when the number of iterations are lower, both validation and training sets have a similar error, but the error is um, quite high in the beginning. As we go ahead, the as the model gets optimized, the the validation error would kind of become fixed, while the training error, the error on the training set, could keep on growing down. Okay, so this is also a sign of overlearning. Okay, as more and more iteration keep on going, we keep on optimizing thetas, that might reduce the error on the training set, but it is increasing the error in the validation set. Okay, so epoch is the number of iterations. Epoch is basically if you have uh, uh, right n number of iterations, we call that epoch. Okay, so you can take a look at the epoch here. I'll just do, okay. So, all right, let me just go up. Here it is. Okay, so what it is doing is it's basically, this is the epoch. Okay, Binta. So this is the epoch. So what we are doing is, let me go up a bit. So here we are generating our input data. Okay, then we are splitting the input data into training and test set. Then we are creating the pipeline whereby we are first introducing polynomial features, 90-degree polynomial features, and then we are scaling the features. Okay. Once done, when we are calling fit transform, this is the data we get, and then we, okay. So we get the scale data with polynomial features and so on. Okay. Now, here what we have is okay. All right. So so we are calling this SGD regressor. We are saying that number of iterations is 1, penalty is none, and then eta 0, the initial eta, is 0.005, and warm start is true. Okay, warm start probably refers to assuming initial value to be higher. Okay. Okay, so SGD regressor probably refers to the warm start. Let me just go down. Okay, when set to true, right, reuse the solutions of the previous call to fit an initialization. Otherwise, just erase the previous solution. Okay, okay. So yeah, I think that's what we're going to talk about. So warm start is basically keep the previous value instead of restarting from the beginning. Okay, that's warm start. And learning rate is constant. We are not varying it. And random state is 42. Okay, so right. So we are saying the number of epochs is 500. Okay, and we are iterating over these number of epochs. Okay, so what we are saying is SGD regressor.fit, and this is our training data. Okay, these are X and Y of our training data. And then what we are doing is we are predicting Y values. Okay. And then we are appending the error to a array to the arrays of training error and validation error. So we are preparing the array of array containing training error and validation error. Okay, why? How? First, we are whatever we have predicted just now, we are subtracting that. Okay, so why well predict that we have done. Uh, okay, yeah. So y training prediction that we have done on training data, we subtracted from y training. Okay. Similarly, we do for the validation. So we find out what are the training error and validation errors. Okay. So what we are doing here is we are iterating over various values. Okay. And on every iteration, we are maintaining the training error and validation error. Okay. So, so once this is done, we are saying what is the best epoch, meaning find that index in the array for which validation error was the minimum. Okay, now, okay, similarly, for this particular index, we are finding that value which was the error and we are computing the square root of it. That's our best root mean square value. Okay, so these are the two things we found, that what is that index on which best value occurred and what is the best value. Okay, then we are saying plot dot annotate. Iteration is same as epoch. All right, so best epoch, best index as in best instance or best instant. Epoch is generally referred as instant in most of the communication. So here we are saying that plot this data with x being this, y being this, and so on. Okay, and yes. So we are annotating this, and also we are plotting these two records. So we are plotting these. Okay, so we're plotting this, we're plotting training errors, and so on. So this is the outcome of our work. All right. So basically, what we have done here is we have shown that if we keep on increasing number of iteration, what starts happening is the error starts increasing. In the validation, error starts increasing. So here, um, right? So there was a question regarding the warm start. Warm start essentially here, when we enable warm start, what it does is in uh, each of the what do you say? Each of the prediction, whenever we are doing the prediction, okay, whenever we are doing say training here at this point, in each of the iteration we are training it, correct? So instead of starting the coefficient again from the beginning, continue from it. That's what warm start means. Okay, warm start means continue from the point where we left off previously. Okay, so using this technique, we have done this optimization. Now, so what we are trying to demonstrate is that if we start doing more computation, the chance of getting a good model becomes lower. Okay, or we kind of worsen the model by increasing the number of iteration. This happens in some cases, and this is more true in case of the high degree of polynomial. That that as the iterations keep on going, the separation between validation and training set keeps on increasing. Okay, as the epoch increases, the algorithm learns and the root mean square error on the training set keeps on going down, and so does the prediction error on the validation set. Now, after a while, the validation error starts increasing. This indicates that the model has started to overfit the training data. So ideally, the moment the root mean square error kind of stabilizes, just stop at that point. we should just stop as soon as validation error has reached the minimum and stays there for some time. Okay, so in the previous example, the batch gradient descent, the curve was smooth. Okay, that's why we could locate the minimum easily. Okay, it was easy to locate the minima visually. But with stochastic and mini batch, you remember that there was no such smooth curve. It was continuously jumping back and forth, right? And it is hard to know where is that stabilization point, where is that minima point. So therefore we need to figure out some way of identifying it. So one solution is to stop only after the validation error. So one solution is to stop when the validation error stays there for some time. Okay, so has been there above minimum for some time. So if your validation error is there as a minimum for quite some time, then you keep it there. Otherwise, you roll back the model parameters to the point when the validation error was at minimum. Okay, so that's what we basically keep the record of, as in we keep on moving the way we do the minima, right? The way we do the minima computation, that if the current value is minimum, then keep this, otherwise keep the older one. Similarly here, if our minimum value, we have reached the minimum value and minimum value has stayed for some time, then we basically keep on updating our results and declare that to be a early stopping, or we declare that to be a solution. Okay, so this is what is the, all right. So we, so this was another technique called early stopping to avoid the overfitting. So so when we keep on going on iteration for a longer duration, what it starts doing, it starts memoizing the data, memoizing the training set, while increasing the error on the validation set. In those cases, what we should do is we should stop as soon as we hit the minimum point. And one way to figure this out is by keeping note of the recent few data points and see if we have stayed on the minimum for some time, and otherwise we continue. All right. A question from Gopi: would you suggest a combination? Would you suggest using a combination of early stopping and regularization? Yes. Okay. So you should consider using a combination of early stopping and regularization. Okay. The way we do the early stopping is by the way of computing the minimum point and then comparing with the past minimum points. All right. So yeah, so that was about the early stopping. Okay. So in the next session, we are going to start with logistic regression. Logistic regression is very similar to the linear regression, just that the objective function is going to be 0 or 1. Okay. So we will learn the logistic regression in the next session. So what we learned was we learned that using linear regression we can solve all kinds of polynomial regression, and we can also fix the we can also make it more stabilized using regularization parameters, and we also learned the other techniques of regularization. All right. So we will continue from logistic regression in the next session. Okay. Logistic regression is basically a classification problem. So if we have to classify things into many buckets, we use logistic regression. A question from Vinta is float of INF minus INF. Okay, so which part are we talking about? Not yet. Decision tree is a separate chapter, Pavan. So we are going to go into the whole chapter. It's a separate chapter, just like linear regression. Okay. All right. So thank you, everyone. We had a wonderful set of questions. All right. A question from Binta is this. Let me just answer this question. It's a very important question. All right. I think, yeah. So whenever we are starting, we start with infinite value. Okay, because any value is going to be smaller than the infinite, correct? So I'll just show you this. So let's say we started here, okay? So, okay, so it's really huge value, okay? It's infinite, right? So is it greater than, or let me just say something like this, okay? So even this, if you see, this is true, meaning every possible number is smaller than this. Therefore, in the first iteration itself, it will get updated. If the validation error is lesser than the minimum validation error, then this value will be updated. All right? Is number of iteration 500 or 1? I'm confused. So here, this is the iteration parameter. So it starts with 1, then it keeps on going till 1000. Yes, that's right, Binta. INF represents infinite. Okay. So our question is, yeah, let me answer this. So whenever we are calling SGD regression here, okay. So, all right. So I think, yeah, we are just calling it one iteration. Interesting. So since we are iterating ourselves and we are maintaining the previous coefficient, that's why we just iterate once. Okay. That's the number of iterations that we're doing. Okay. The reason why we are using such a small number of iteration is we are basically maintaining the previous coefficients and just moving one step. Okay. Moving one step. And we are iterating, the main iteration is happening outside. Yes, probably in order to do the plot. That's correct. Okay. So we are using these things, the two things in conjunction. Okay. A question from Noor is, in the early stopping, our objective is to find best minimum error. What is the objective in terms of the ridge, lasso, and elastic? Again, um, uh, there the idea is, again, in case of ridge, lasso, and elastic, we want to minimize the error in order to find the model parameters and use those model parameters for the predictions. All right. Great. Great set of questions. I look forward to see you next week. All right. And great. Great to have you in the session. I hope you are liking the session. I have kept the session to be a little bit more detailed, as we could have kept it usual, like use the algorithm and that's it, right? But what I believe is that that whatever we are learning in this class is something that is the most important in the career of a data scientist, okay? Because these are the things that actually matter when you are taking decisions on the models, okay? Because learning to use a particular algorithm or knowing what are the libraries available in scikit-learn, it's just one part of the problem, okay? All right. So I hope this is helpful to you. All right. I'm really happy for that compliment, Ross. Thank you so much. I'm sure that this course will be helpful. And since we started with, when we were doing the time computation, we were thinking that we will go over less over the detailed concept, but it so happens that we realized that it's important to understand the concept in detail. That's why time might have become little more. And little more means it has increased by 2x. So I'm really sorry for that increasing your time. Okay, but I think whatever we are learning is going to be useful to all of us, and it's going to be worth your time. All right. So thank you, Shahrukh, Ross, Noor, Kamal, Gigi, Bintao, Balaji, and Abhinav. I look forward to see you next week. Bye bye. Wonderful, wonderful to have all of you in the session.